Hello dear students, learners and participants. I welcome you all to the 8-week online module on digital electronics and its applications organized by Department of Electronics and Telecommunication, Government Polytechnic Hingoli. So in this week, we are focusing our study on assembly language programming using 8086. These lectures are presented by Shailendra Balumote, lecturer in electronics, Government Polytechnic Hingoli. In this video lecture, we are going to study the addressing modes of 8086. Addressing modes for register and immediate data, addressing modes for memory data, addressing modes for input-output ports, and relative addressing modes. At the end of this video lecture, the students will be able to select relevant addressing mode of 8086 to identify instruction for solving the given problem with justification. So in previous part we have seen that program is nothing but it is a set of instructions and each instruction contains an operand. So every instruction of program requires to operate on a data for its execution. This data or operand is stored in a particular location of memory of your processor. To access this data, we have to use different ways. The different ways in which a source operand is denoted in the instruction are known as addressing modes. In 8086, there are 12 different addressing modes and which are categorized into 5 different groups. So we'll see one by one. First group is addressing mode for register and immediate data, which includes register addressing and immediate addressing. Second group is addressing mode for memory data, which includes direct addressing, register indirect addressing, based addressing, indexed addressing, based index addressing, and string addressing. Group 3 is for addressing modes for input-output ports. So we can access the input-output ports through direct input-output port addressing or indirect input-output port addressing. Group 4 is relative addressing mode, which includes a single addressing mode known as relative addressing. And the last group is implied addressing mode, which includes a single addressing mode known as implied addressing mode. Now we'll start discussing these different addressing modes one by one. First is a register addressing mode. Now in this addressing mode, the instruction will specify the name of the register which holds the data to be operated by the instruction. So we'll see this example. Move CL, DH. The content of 8-bit register DH is moved to another 8-bit register CL. We will elaborate this with an example. Now consider this is our DH register, DX register. Lower part is DL and upper part is DH. Similarly, this is our CX register. Lower byte is CL, upper byte is CH. Now we'll assume a random data here 4823 and CH will contain 4146. Now after execution of this instruction move a CL, DH, the data of the DH is moved to the CL. Now the updated value of CL will become like this. So CH will remain as it is. It will remain 41 and the CL will become 48 now. The second addressing mode is immediate addressing mode. In immediate addressing mode, an 8-bit or 16-bit data is specified as a part of instruction. See this example, move DL, 08H. So here the 8-bit data 08H given in the instruction is directly moved to the DL register. Take another example, move AX, 0A9FH. So here AX is a 16-bit register, so we can move a 16-bit data 0A9FH into this AX register. We will see this example. Consider this first example. Let's say this is our DX register. Now this DL initially contains A, B, this hex value. Now after execution of this instruction, the data 08 is directly moved into the DL register. We'll consider the second example. In second example, this AX is a 16-bit register. Suppose initially AX contains 1, 2 and A, B, this data. After execution of this instruction, the value of AX becomes 0A9F. So in this way, this addressing occurs. Before moving to the next group of our addressing mode, which is used to access the memory, we will revise how to generate a physical address. Now, for physical address generation, we will require an offset value which is stored in the pointer or index register. Then a segment register value which is 16-bit value, and this 16-bit value is shifted to the left by 4 bits. Now these two values are added by the adder and the physical address of 20 bits is generated. Now the address bus of 8086 is a 20-bit address line. So it can access memory up to 2 to the power 20, that is 1 megabyte of memory. Now the largest size of register is only 16-bit. So to generate a physical address, we will shift the segment register by 4 bits to the left and it is added with the offset value to generate a physical address. Here see the example. The memory address represented in the form as below. It specifies the segment, then colon and offset value. So we will consider one example, 89AB colon F012. So 89AB is a segment register value and F012 is a offset value. Now to calculate this physical address, this 89AB is shifted to the left by 4 bits. Offset value, which is F012, is added into this and we will get 98AC2, which is the physical memory address of the given location. Now the next addressing mode is a direct addressing mode. In the direct addressing mode, we will specify a memory location in the square bracket. So here the effective addresses of the memory location at which data operand is stored is given in the instruction. The effective address is just a 16-bit number written directly in the instruction. So see this example. Here the instruction is written as move bx, 135h in the square bracket. So suppose this is our memory and in this memory at 1345 location some value is there. Now this value is copied into the BX register. Move BL, 400H. Similarly, the value which is stored at memory location 400H, suppose it is A, B. This value is moved in the BL. The square bracket here around the 1345H denotes that the content of the memory location when executed, this instruction will copy the contents of memory location into the BX register. This addressing mode is also called direct mode because the displacement of the operand from the segment base is specified directly in the instruction. The next addressing mode is register indirect addressing mode. So in this mode, the name of the register which holds the effective address is specified in the instructions. Registers used to hold the effective address are any of the following. So we can use BX, BP, DI and SI registers to hold the effective address, and the content of the DS register is used for the base address calculation. See this example, move CX, square bracket BX. So in this operation, first we will see how to the physical address is calculated. Effective address is stored in the BX, that is nothing but offset value. Then base address is stored in the data segment register. Now this data segment register is multiplied by 16 decimal, which is nothing but shifting the number by the 4 digits to the left. So the memory address is equal to base address plus effective address. Now this shifted data segment value and BX value is added to generate the memory location. Now this memory address, at this memory address some value is stored in the memory. That value is copied into the CX register. Now the CX register is a 16-bit register. So here if the value at address is copied into CL, then the value of address plus 1 is copied into the CH register. If we are accessing the 8-bit, the next addressing mode is based addressing mode. In the based addressing mode, the base register BX or base pointer register BP is used to hold the base value of the effective address, and 8-bit signed or 16-bit unsigned displacement will be specified in the instruction. In this case of 8-bit displacement, the sign extended to the 16-bit before adding to the base value. When BX holds the base value of effective address, the 20-bit physical address is calculated with the help of BX register and data segment register. When base pointer register holds the base value of effective address, then base pointer and stack segment registers are used to calculate the 20-bit physical address. See the example given here, move AX, square bracket BX plus 08H. So BX holds the effective address and 08 is the signed displacement. Now this sign extension to convert it into 16-bit is added here. So we will get 0008 as the displacement. Now the effective address is calculated as BX plus 0008 and the result is stored in BX register. Now the base address, as we are using the BX register for effective address, the base register will be the DS register or data segment register. So data segment register value is shifted 4 bits to the left by multiplying by 16, and the physical memory of 20-bit is calculated with base address plus effective address EA. Now the value which is stored at the physical memory location is copied to the AX register, or this can be performed as the memory location's value is copied into lower byte of the AX and memory location plus 1's value is stored in the upper byte of the AX register. The next addressing mode in the addressing mode for memory data is indexed addressing mode. In indexed addressing mode, we are going to use source index or destination index register to hold the index value for the memory data. And as previously we have seen, the signed 8-bit or unsigned 16-bit displacement is specified in the instruction. Now the displacement is added to the index value in source index or destination index register to obtain the effective address. In case of 8-bit displacement, it is sign extended to 16-bit before adding to the base value. See the example, move cx comma square bracket si plus 0a2h. So si holds the effective address and 0a2h is the extended, it is the displacement explained here. So we have to convert this a2 into the signed extension to the 16-bit. So we are adding ff to this a2, so we'll get the value as ff_a2. Now effective address can be calculated as the value held by the source index and the displacement. So si plus ff_a2 will give you the effective address, and the base address is calculated from the data segment register. So this data segment register value is shifted by 4 bits to the left, that is multiplying by 16 decimal. The 20-bit physical memory address is calculated by adding this base address value and effective address value calculated. Here when we execute this instruction, the value stored at the memory location is copied into the CX register, or when we are performing 8-bit or operating on 8-bit memory, then the value stored at memory address is copied into the lower byte of CX register, that is CL register, and next memory address location's value is copied into the CH, that is higher byte of the CX register. So the remaining addressing modes we will see in the next video. Thank you.